Hello, Internet. Today we're going to be taking a look at this ship thing that I have, and the idea here is we want to make it so it can move. I've already done one, but I want to do two other types of moving it because this one is very Space Invaders, and that doesn't look like an actual ship should. Um, so you'll see what I mean. Like we have a ship, it's got thrusters, and you'd expect it to like go in the direction that it's pointing, or at least sort of do that, but it doesn't. So there's a bunch here. I added a gizmo so you can kind of see what I'm doing on a controller, because otherwise it's hard to kind of show what's going on. So let me just remove the movement bit. There's a bunch of components to this little gizmo. The gray outside bit is actually how far it can go out. So it's like a ratio. And then there's a red line and a blue line, which is the X and the Z axis, or the up and the side to side. And then the white thing is sort of a ratio of how full the vector is. So as it goes all the way up, we're all the way off to the side. And then as we ease up on it, it just disappears. So that's sort of how that works. I'll walk you through the code, and then we can start doing the two things. What I'm thinking is I want one so I can push to like the right or the left, like this, and it should turn with that horizontal movement instead of moving left and right. Like right now, it just slides in the direction you point, and that's okay, I guess. But I want it to spin. And so that's one of them. The other one, I want to use a dot product so we can point in a direction and it will figure out if it needs to rotate and add thrust to go in that direction. I kind of talked about that a little bit in the dot products video I did yesterday, so we'll see how that works. But that's sort of what we're doing. This has a few different components. You can see we have a ship input controller here, which has a vertical and horizontal component, which is just reading the inputs. Horizontal and vertical components, just default Unity stuff. And you can see that. There is one thing I'd note. If I disable the movement again, we can go, like you can see here, this is -1 and this is -0.24. So one thing we need to note with dot products, which we're going to be using later, we want to be using normalized stuff. And those aren't normalized. If we turn that into a vector, it would have a length longer than 1. So we'll need to normalize that input just because of the way the controllers work. And it prevents the system from being gamed too, so you can't just plug in something that has like really wide ranges for whatever reason, and just suddenly you can turn and move and do all this other stuff just faster than everybody else. And then the movement controller currently has two components. We'll probably add a third for the turn velocity, or whatever we want to call that. But right now it has a velocity and then a movement type, which is just an enum. And so you can select what you want it to do. Right now it's just a slide. That's the only thing we do. And that just lets you slide around. And then I added trails so you can kind of see where the thrusters have been. And that's that. So let's look at the input controller first. And so we have just two public fields. So a horizontal and vertical. In the update, those are just updated. And that's all that really happens here. There's a bunch of stuff in the onDraw gizmos, which is kind of doing some fun stuff. And so what it's doing is turning those two values into a vector, and then getting the length of that and capping that so it can't go above 1. So that's what this min is doing. If it's less than 1, it's going to take the magnitude, but if it ever goes above 1, it's going to grab that, which is like a normalization, but not actually really normalizing it. It's just working on the magnitude, because I actually want the full length. And then here, we're checking if the size is greater than the float epsilon, which is the smallest possible float value above 0. That probably isn't actually necessary. You could probably just plug in 0 here and it'd still work. But I figured I'd throw that in there because I felt fancy and I didn't really know what it was until I went and looked it up. So that's why that's there. No real reason. And then we draw The gray bit, which is the maximum size, I have hard-coded 4 here because when it was just 1, it was actually overlapping our object, our ship, and that wasn't great because you couldn't really see what was actually happening because it was all happening under the model, and then it was really washed out and just hard to find. So there's a multiplier of 4 here, which is just increasing that. I could move that out and put that somewhere nicer, but this is a gizmo, and I just wanted this for like visual purposes so you can kind of see what the controller is doing without me having to like hold the controller up. And so that's going to be drawn at our ship, and this one needs to be drawn first. Because if you draw this second, if you draw this wire sphere second, what's going to happen is it's going to overwrite. And so if you have like a full length direction, the second sphere, which actually shows the ratio, I guess, is just going to disappear. And I didn't want that. So instead, the outside sphere turns white if it's full. Otherwise, this is going to draw the size of whatever you're doing. And so that's just taking the size that we calculated up here, which is just the length of that vector, and then drawing that. And so that gets us our 2 spheres. And then in here, we draw each of the components separately. So we have a red component that draws the right. This is not based off of the orientation of the object we're using. It's actually world space right. So even if we rotate the object, that should still point to the right. And then we do the same thing for the forward vector. We're working in X and Z space, not in XY space, because this is actually a 3D project, not a 2D project. If you're working in Unity 2D, like if you have your Unity 2D project set up, this won't work, this vector 3.forward. You want to change that to up, because otherwise, Unity 2D is on the XY plane. 3D games typically are on the XZ plane, and that's just the way it works. And so since I'm working in 3D, that's what I did. And then the final one is just a sum of those that takes that original direction vector and then just draws the length of the thing, so you can kind of see where it's going. And that's just sort of that's actually like the cardinal direction that I'm pointing the controller in, and so you can see all of that. And that is the gizmo. That's the hard part. The ship movement has a few components. One is this ship movement type, which right now there's just a slide, so that's the only one we can do. It has the velocity and the movement type as 2 inputs, and a third field that's kind of hidden behind called the input controller, which is a reference to that input controller that we were just looking at. And so we're going to grab the component in start and then do this switch statement in the update, which is going to switch on the input controller type. And so the movement type kind of switches this. The default is just going to be slide, which calls this, which is just a private method that is very poorly optimized, that updates the position twice, once on the horizontal axis and once on the vertical axis. And so it's just going to move you by the input, by the world space right or world space forward, the velocity that we have set, so you can kind of tune the speed, and then the time delta so you don't go real fast. And it's a little bit more predictable. But that's pretty much it. This is not in any way optimized. It's not intended for that. It's strictly designed so we can kind of get all of the components isolated and kind of isolate what's going on and what's happening where. Ideally, we wouldn't have 2 of these, but we do. And we're not going to fix it. So that's that. Again, with if you're using Unity 2D, this forward needs to be an up, because again, different planes. So what we need to do is add a new movement type. So let's do rotate on horizontal. Oh, manual rotation? I like that name. Sure. So we have a manual rotation case. Let's just add that up here and do case ship movement type dot manual rotation, and we'll do an update move manual rotation like so. And this is a switch statement, so we need to break out of it. I'm just returning out of these and just exiting out, because there should be nothing else that follows it. And so that is that function. Now we need to actually implement it though. And so the first bit is really easy. We can actually just take one of these and plug it in here. So instead of doing the input controller horizontal, I actually want the vertical. And then instead of this, vector 3.right, I actually want the ship's forward vector, which is going to be this transform.forward, which is going to be the direction that our ship is facing. And so that should move it forward. And so if I start this, I should be able to switch over and have a manual rotation movement type. It's already running. Let's stop that manual rotation, restart. Cool. And then I should be able to go left and right. You can see it's growing and things, but as I go up and down, we actually move along our forward axis, which is that way. And so now we just need to rotate it. We have the horizontal thing, and for rotation, I think I'm just going to use Euler values because I can. And we don't really have to worry about a lot of the problems you can run into with rotation like this. I've talked about this in other videos, but 3D rotation can get really complicated if you're not careful. It's just an ongoing problem. That's why we work with quaternions instead of just 3D vector space. But for this, we're only rotating in one axis, so it shouldn't become a problem. We're just going to be working on the y-axis, so we can kind of spin, but we can't like do dives or yaws or pitches or whatever those other things are. We don't need to worry about that. So instead, let's do a quaternion, not Euler. And what we want is we want 0, this transform.rotation, Euler angles.y. So we're taking the current angle and another z, and that is our rotation. That actually isn't like rotating anything. All that should do is get us the exact same thing, except we're zeroing out the x and the z. So we can give this like 180 degrees or whatever, and we'll rotate around, but whatever. Y rotation is going to be a rotation around, like, imagine jabbing like an axis through the actual object in our scene. Since we're looking along the y-axis, we're literally sticking the axis right through the object so we can spin the entire object. So float, we need to actually like calculate the rotation. So let's do a rotation amount, which is going to be rotation speed times a time delta, time.delta time, times something else, the input controller dot horizontal, which is our horizontal movement. And so rotation speed, like so, needs to be actually created. So float, rotation speed, cool. And that should be all we need to actually rotate this thing, right? I think I did that right. Hold on. Did I actually add it? No, I did not. We need to add it to here. Otherwise, the rotation amount isn't actually used anywhere. So rotation amount. Cool. And just for fun, let's turn that into a var. Vars in C# are just auto-assigned. So the type automatically gets assigned. You can see it still thinks it's a float. We just don't have to say it's a float. So if we ever want to change it, we can. And that's just sort of a convenience thing. It keeps you from having to do a lot of extra factors if you ever change the types. And you don't really have to think about it too much as long as your IDE kind of can keep up. So, fun little trick. Let's do that. We need an actual rotation speed in this, otherwise this is not going to work at all. This rotation speed should be a measure of degrees per second that will rotate at maximum speed. So like 60? So we can do like a 180 in 3 seconds, right? I think that makes sense. We'll see. If it's in radians, this is going to go real fast. So we can go forward and backwards. And if I hold right, our horizontal is being seen, but not doing anything. And we have no rotation at all. Did I save? I did save. Oh. 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 We were multiplying, and our original y angle was 0. So 0 times anything is just going to get us back to 0, and then we just keep doing 0 again and again and again and again and again and again. So that's not going to work for anybody. So let's change that and try this again. This should actually work this time. So hold right, and we turn right, and then hold left, and we turn left. And you kind of get the idea. And if I hold forward now, we go in that direction. The problem with this is it's really unintuitive. I'm holding up on the controller, and we're going down. And that's just, it's really hard to keep track of. Maybe it makes some sense, but I don't know. It's kind of like a preference thing. For me, this is not super intuitive. You can kind of work it out, and it kind of makes sense. But I kind of, with some of the experiments I've done in the past, using dot products can kind of help bring this out and make it a little bit more intuitive. And so what we're going to do is make a third movement type, which we'll call adaptive rotation. Sure. Major question mark on that name, but we'll just ignore it. Case ship movement type dot adaptive rotation update move adaptive rotation, like so. Return. And so that's just going to get out of there. Let's copy what we have for the manual rotation, because really all we're doing is changing this rotation amount. That's the big thing that we're kind of changing. We're actually going to change this one too, but for the most part, it's going to be that rotation amount. And so what I actually am going to need for this to work is a few vectors. One, we're going to need a vector 3. Let's just do the var thing again. And so this is going to be our input direction. And so this is a new vector 3 with the x equal to our horizontal. Horizontal 0, because again 3D space. If you're in 2D, change that to be this one, which is going to be the input controller dot vertical, and that is sort of the input space we're working in. The cool thing with this is now we have vectors, so we can do all sorts of vector stuff with it. Since I've kind of alluded that we're going to be using dot products, we're going to be using dot products, and so what we want is a thrust. So we'll do var thrust, which is going to be equal to our vector 3 dot. So we're going to take the dot product of two things. Our input direction. We want the normalized vector out of that. I should probably normalize these separately. Let's just do normalize. That won't work, actually. Hold on. I still want the strength to come out of this. So if I normalize this vector, we'd have to recalculate everything, and I don't want to do that. So we're going to leave that way, and this will be inefficient, and we can look at how to do that after we get it actually working, which I think makes more sense anyway. So we'll do that. So anyway, going back to this, we're taking the dot product of our input and our transform. So this dot transform dot forward. And so our thrust is actually calculated by the difference between our normalized direction, so the input of our controller, and the direction we're facing already. So if those are in line, our thrust will be 1, for example. If they're in opposite directions, our thrust becomes -1. And so we'll go backwards. And so that's sort of how the thrust can kind of get calculated. The cool thing is we can do this for the rotation as well. But we don't want the forward vector, we want the right vector. And so this one is going to say, is the controller aimed to the right of me, or to the left, or whatever? And if it is, then I need to rotate to get to that point. And so rotation comes in here, And so instead of doing input controller dot horizontal here, or thrust or whatever, instead of doing anything for the rotation amount, we can just plug in that dot product and that becomes our rotation. And same thing here for the vertical, we can just plug in the thrust. And we need one other thing, which is going to be our input direction.magnitude. So this is getting a bit long. Just to keep it all on the same page, we'll do that. I don't know if that's helpful or not, but there you go. So that is our forward momentum, which is going to be our thrust times the magnitude of our inputs, and then everything else. The rotation amount is going to be calculated the exact same way. So rotation speed times that times the rotation, which we're getting up here. And that should be everything, right? I don't think we need anything else to make this work. And so it'll either work or I screwed something up, and then we can figure it out. But the general idea is we're comparing the direction of our controller to the direction of our ship. And so as those become in line, we can just thrust to go in that line. But as they diverge, as they go more perpendicular, we'll want to turn to do that. And so the dot product is going to help us kind of solve that, because it becomes 1 when you're comparing two normalized vectors and they're in line with one another. And it becomes 0 when they're not. So we'll have no thrust if we're trying to point our controller in a perpendicular direction to our ship. We'll just get a rotation. And then it will adapt as the ship becomes in line with what the controller is thinking. So you'll rotate and start accelerating as that happens, and it should kind of automatically adapt without you having to actually do anything. It won't be perfect, but it should be close. So let's see how that works. And hopefully it's a little bit more intuitive. This is kind of something where you have to actually use it. So try the source and see how you like it. But you can kind of see, I'm holding, that's not right. Is it calling the right function? It feels like it's not, because I'm holding left and it's just rotating. So I think we might still be using our old function. Update move manual rotation. Oh, oops. I see. We should probably switch these, huh? So this becomes our manual. Manual rotation and our adaptive rotation. Let's actually spell this right. Manual, that's not how you do that. And so, if we don't actually screw up our function names and do everything wrong, now it should work, right? And if not, then I'm gonna feel real silly, because I've already screwed this up once, so it can't go much worse. Right? Yeah, we'll see. So up and down, we still go forward and backwards, but if I hold left, you can see we turn and then start accelerating more and more. And if I hold right and kind of down, we'll go backwards and do that and start actually turning towards to go back around. Go down, kind of do that. And so you can kind of see, if you follow that white line, that's sort of where I'm trying to turn it. And we kind of do this, and we get this very clear motion without having to actually do that much work. And it looks fairly good. Like, I didn't change the controller at all, and it did that whole complex move. We can increase like the rotation speed to get different stuff, and we start doing more cool things. But I'm really not thinking about this too much, which is pretty cool, because I can like watch the camera and this seems to work. So that's sort of how you might use dot products to kind of make this work. And you could do this for cars or other things as well to kind of get that same thing, which might make sense for, say, a mobile game where the only input is like a player's touch. And you want them to like drag a controller around to control a ship in a complex way. This removes a lot of the complexity of having to manage rotation and speed and things like that, and puts it all in a single joystick. So that's two solutions, I guess, to movement in 3D-ish, 2D top-down space that kind of works for vehicles. And I'll put the source somewhere so you can check it out and play with it yourself and see how to use it. If you haven't already, checked out the video I just did on dot products, which kind of walks through some of how to use that and a little bit more about what they're actually doing. But yeah, that's it for this video. So if you want to, there was something I was going to say and it just totally went out of my mind. But that's it for this video. So until next time, see you, internet.